Today we're going to be working on our test review for the derivative function. In question number 1, it says to use the limit definition of the derivative to determine f prime of x if f of x is equal to 3x squared minus 5x plus 2. So I'm going to start out by writing our limit definition. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. And so what that means is that I'm going to start here with f of x plus x. I need to substitute x plus h in for x into my function. So I'm going to have 3 times x plus h squared minus 5 times x plus h plus 2. And that is f of x plus h. Now I need to subtract f of x. And we're going to keep this all over h. So if I do a little algebra here, we're going to get 3 times an x plus h squared. That's our binomial squared that we've been working on, x squared plus 2xh plus h squared. And we can go ahead and distribute the 5 minus 5x minus 5h plus 2, and then this minus sign needs to be distributed to f of x. Minus 3x squared plus 5x minus 2 all over h. In the next step, I'm going to distribute that 3. So we'll have 3x squared plus 6xh plus 3h squared minus 5x squared minus 5h plus 2 minus 3x squared plus 5x minus 2, all still over h. Now we're to the point where things should start canceling out. Notice I've got 3x squared minus 3x squared. Those can cancel out. I have negative 5x and positive 5x. Whoa, where'd that squared front come from? Looks like I made a little mistake there. Let's get rid of that squared. It should not be there. And my 2's cancel out, 2 and negative 2. So I'm left with the limit as h goes to 0 of 6xh plus 3h squared minus 5h all over h. Now remember, the point of all of this is to be able to get this h in the denominator to cancel out, because when I substitute 0 there, it gives me something that's undefined. Well, in the numerator, every term has an h, so I can factor it out. And that leaves me with h times 6x plus 3h minus 5. And now my h's can cancel out. And if we remember, this is a limit as h is going to 0. If I plug 0 back in for this h right here, then that term is 0, and we're left with 6x minus 5, which is the correct answer. Question number 2. Let f of x be the function defined by f of x equal to x cubed for x less than or equal to 0, and x whenever x is greater than 0. Which of the following is true? Well, for me, I would just sketch a quick graph before I start to look at the multiple choice questions. X cubed up to 0 looks like this, and then y equals x for x greater than 0 is like that. So we have a strange looking graph here. Let's check out our multiple choice answers. Question A, f of x is an odd function. Well, if I consider each of these functions individually, they are odd functions as long as we're including all real numbers. But since I'm only graphing x cubed for x less than 0 and x for x greater than 0, we do not have an odd function. Odd function means origin symmetry, and I don't have any symmetry here. So that is not true. Answer B, f of x is discontinuous at x equals 0. Well, this is not true. Our graphs are connected there at 0, 0. We do have continuity, so that's not true. F of x has a relative maximum point. If you notice, this function is actually always increasing. There is no maximum point, so that is not true. Answer D, f prime of 0 is equal to 0. So this is a question about the derivative of f at 0. Now if you notice, to the left of 0 I have a curve, and to the right of 0 I have a line. That means that right here at this point we do have a sharp turn. A sharp turn means that no derivative exists, and if the derivative does not exist, then it certainly cannot be equal to 0. So that is not true. Hopefully our last choice is true. F prime of x is greater than 0 for x not equal to 0. If you remember from our chart, if f prime is greater than 0, that means that f is increasing. And if we take a look at our graph, f is in fact increasing for all values, excluding 0, because of course at 0 f prime does not exist. So we have to exclude it, and if we do, then for all other x, the function is increasing, and that is our answer. Question number 3, we have a graph of f prime of x. Notice this is f prime. It is the derivative of f, shown in the figure above. Which of the following describes all relative minima and relative maxima of f? Now if you look at your chart, you'll see that whenever f has a relative maximum, if f has a relative maximum, that means that f prime is equal to 0, and it's changing from positive to 0 to negative, because if f prime is positive and then negative, that means that f is increasing and then decreasing, which would give me a maximum. And if f has a relative minimum, then f prime again is equal to 0, but it should be negative and then 0 and then positive, which would indicate that the graph is decreasing and then increasing. So if I go to my graph of f prime, I'm looking for the zeros, and I see that there's 3 of them. At this first 0, my graph is negative and then positive. And if we remember from the chart, that means that this point is a relative minimum. At the second 0, my graph is positive and then negative, which means f has a relative maximum at that point. And finally, at the last 0, my graph is negative and then positive, which gives me another relative minimum. So I have 1 relative maximum, 2 relative minima. Answer A. On question number 4, which of the following pairs of graphs could represent the graph of a function and the graph of its derivative? Well, let's check out this first pair of graphs. If we consider this graph, it is always increasing, which means f prime should be positive. It starts out rather flat or close to 0, and it ends up steep or far from 0. If I look at this graph, it is always positive. It starts out flat, close to 0, and it actually ends up steep or far from 0. This graph could actually be the derivative of this graph. And you may remember from class that we explored y equals e to the x, which is what this graph is, and we discovered that its derivative is in fact itself. It's the only function for which that is true. So choice number 2, we have a parabola that is opening downward. Now hopefully you might think that the derivative of a parabola should be linear, and that's not what we have here in the derivative graph. So this one's probably not going to work, but let's check it out. Here on my parabola, notice I have a maximum point on the graph, which implies I should have a 0 on the derivative at that point. Right there you can see that this graph is not the derivative because I don't have a 0 slope at that point. My graph is increasing and then decreasing, which means my derivative graph should be positive and then negative. It should look something like that, and therefore this one does not work. In the final graph, again I have a maximum point right here, which means I would be expecting a 0 in about the same place, and I seem to have one of those on my derivative graph. This function is increasing and then decreasing, and I have a graph that is positive and then negative, and so this graph works as well. The pair of graphs in number 1 and the pair of graphs in number 3, they both work. They both show a function and its derivative. Question number 5, we have another graph, and it says that this is the graph of f of x. So let's make note of that. We are looking at the function. Question A says, for what values of x, if any, is the second derivative negative, positive, and 0? So we need to remember our chart. If the second derivative is negative, that means that f should be concave down. If the second derivative is positive, we're looking for f to be concave up. And if the second derivative is 0, we might be expecting an inflection point. So let's see where these things are true. For the second derivative of x less than 0, I would say that this graph is concave down maybe from -1 to 4. Now, I think it is arguable where the inflection point here is. If you said the inflection point is happening here at 0, I think that's fine. I'm going to say it's happening at -1. And so the second derivative of f less than 0 on the interval -1 to 4. The second derivative is greater than 0 wherever this graph is concave up, which would be this part of the graph here from -4 to -1. And if that is true, then our second derivative is equal to 0 where we have the inflection point, which would be right here at -1 where the concavity is changing at x equals -1. Again, if you said that inflection point is happening at x equals 0, that's fine. I think my graph is a little ambiguous. It will not be that unclear on the test. Now in question B, they're asking us to rank the following values in increasing order. F prime at 0, f of 2, f prime of 2, and f double prime of 2. So let's start with f prime at 0. That means I want to know what the slope of the graph is at 0. So that's this point right here. My graph is increasing, and so I have a positive slope. It seems to be about 1. I would guess a slope close to 1. F of 2, this just means the value of the function at 2. So if I look up 2 and I go up here to the function, it seems to have a value of 2. F prime of 2 means the slope of the graph at 2. And if this is my point where x is equal to 2, it looks like the slope of that graph would be 0. We seem to have a relative maximum there at 2. So I would say the slope of the graph is 0. And then finally, the second derivative at 2. If I look at the graph where x is equal to 2, my graph is concave down. Remember, the second derivative tells us about concavity. If my graph is concave down, that means that this has to be negative. So therefore, if I list them in increasing order, the second derivative at 2 must be the smallest because it's negative. The next value would be the slope, first derivative at 2, because it's equal to 0. The next value would be the slope at 0, because we said it was approximately 1. It's certainly less than 2. And so our greatest value would be f of 2. Question number 6, we had a little issue with this question. I actually rotated the graphs because it seemed that some of them were upside down, but then I noticed that not all of them are upside down. I rechecked the book and they were printed incorrectly in the book. So let's make the best of this. You may notice that the graphs I'm showing here are upside down from what you're looking at. So let's consider this first graph, which would be your final graph. If you notice, we have here a quartic function, or a function with a power of 4, and then there's also a cubic function, or a function that has the power of 3. One thing that we're looking for to identify a function and its derivative, I like to look for zeros first. And if I look at the graph that I traced in orange, I have a minimum here and a maximum at this point. And for neither of those points do I have a 0 on the other graph, which is what I would expect if the purple graph was the slope graph. If the purple graph is the function graph, however, notice at this point here I have a maximum, and that corresponds to a 0 on the orange graph. Right in here, I have a minimum point, which corresponds to a 0 in the orange graph. And then there seems to be another maximum right here, which again corresponds to a 0 on the orange graph. So that would seem to indicate that this is our function and this graph is f prime. Let's look at the next two graphs. Here I have this graph, which seems to again be a quartic graph. And then there is this graph, which looks to be a polynomial with a power of 5. Again, we can check zeros, and don't assume that I use the same color for function and derivative. If I check the zeros on the orange graph, if I check for max and mins on the orange graph, here I have a maximum point, which corresponds to a 0 on the purple graph. If I continue on the orange graph, I have another minimum point right here, which again corresponds to a 0 on the purple graph. I continue to this point where I have a maximum corresponding to a 0 on the purple graph, and finally a minimum, which again does correspond to a 0 on the purple graph. And so the zeros match up, but this is one of those graphs where the purple graph should really be going in the other directions. Our directions are not correct, the graph is wrong, but we can confirm just by zeros alone that this would be our function graph. Sorry, I think I wrote f prime. That would be the function graph, and the purple graph in this case would be our derivative. Finally, in the next graph, we have a parabola and a line, and hopefully we know by now that the derivative of a parabola should be linear, but we can double check with the max mins and zeros. I have a maximum on my parabola at this point, which corresponds to a 0 on the line. This is in fact the function, and the line is f prime. In our final graph, we have this function and this function. And again, if I'm checking for maxes and mins and zeros, if I look at the purple graph, I have a minimum here corresponding to a 0 on the orange graph, and I have a maximum right here which corresponds to a 0 on the orange graph. And so the purple graph is my function and the orange graph is my derivative. My apologies for such a confusing problem, but I hope that I was able to make some sense out of it for you. Question 7. The temperature in degrees Celsius of the water in a pond is a differentiable function. Remember that when they tell us differentiable, we should also assume that means the function is continuous. The table below shows the water temperature as recorded every 3 days over a 15-day period. Question 7, calculate the average rate of change of the temperature of the pond over the 15 days. Now when we see average rate of change, I really want us to immediately start thinking this formula. W of 15 minus W of 0 over 15 minus 0. Again, it is slope formula using function notation. And I'm just going to substitute in values from the table. W of 15 was equal to 21. W of 0 was 20. And 15 minus 0 is 15. And if we do that math, we get 1 over 15 degrees Celsius per day. Now obviously that's not a lot of change, and the data in the table seems to indicate that more radical change was going on. But if I'm just comparing the temperature on day 0 and the temperature on day 15, there is very little change, which makes my average rate of change very small. In question 8, they ask us to estimate the rate of change of the temperature of the pond on day 7. Well, if I look at my table, I don't have a day 7. The two numbers available on the table that are closest to 7 would be the 6 and the 9. So I'm going to calculate W of 9 minus W of 6 divided by 9 minus 6. And this is going to give me an approximation of the rate on day 7. If I substitute in numbers from the table, W of 9 is 24, W of 6 is 28 over 9 minus 6, and we get negative 4/3 degrees Celsius per day. We ended up with a negative rate, which indicates that our temperature is decreasing around day 7, which should make sense if we consider that on day 6 it was 28 and then on day 9 it was 24. Next question. A function is continuous but not differentiable on the interval AB. Which of the following statements must be true? Now we have to be very careful on questions like this because they may have statements on there that could sometimes be true, but here they are asking which one must be true. So we know that the function is continuous, not differentiable. Now before we even read the choices, I want us to remember what this means. Not differentiable, the derivative fails to exist. That means that we either have some discontinuity, a vertical tangent line, or a cusp or sharp term. Those are the 3 things that not differentiable means. However, they'd already told us that the function is continuous. So obviously, discontinuity is not an issue here. Let's check out our choices. Answer A, the function has an asymptote at some value C such that C is between A and B. An asymptote would imply discontinuity, and they've told us that the function is continuous, so that is not the right answer. The limit as x approaches c of f of x does not exist for some value c such that c is between a and b. Well, they told us that the function was continuous, and we know that part of the definition of continuity is that the limit as x approaches c of f of x must exist. If the function is continuous, it's going to exist for every point in between a and b, and so that's not the answer. F of c is undefined for some value c such that c is between a and b. Again, this is a tenet of the definition of continuity. The limit as x approaches c must exist, but also f of c must exist. That's what continuity means, and so that answer choice is not true. Answer D, the function has a cusp at some value c such that c is between a and b. That is the only one that could possibly be true, and so our answer is D. Question 10. Now this starts our free response type questions. On the test you will have a free response question like this and then one like question number 11. On this one we have a test plane flying in a straight line with positive velocity in miles per minute at time t minutes, where v of t is a differentiable function and selected values of t between 0 and 40 are shown in the table. And they're asking us to use the data to find an approximation for v prime of 18. Show the computations, using appropriate units, explain the meaning. Well, if I'm looking for the slope of velocity at 18, or in other words, the acceleration at 18, I'm going to use these two pieces of data, 15 and 20, because those are the ones that are closest to 18. So I'm going to say v of 20 minus v of 15 over 20 minus 15. And then we'll plug in the values from the table. V of 20 is 4.5, v of 15 is 7.0, and 20 minus 15 is 5. And so that's equal to negative 2.5 over 5, or negative 1/2. And then let's put let's put units on this. Our top numbers, those are velocity numbers in miles per minute, and then our bottom numbers 20 and 15, those have units of minutes, and so negative 1/2 miles per minute if you want to say, or we can say per minute squared. And what this means is that at time t equal to 18, the acceleration, or you could say the rate of change of velocity, is approximately negative 1/2 miles per minute squared. Question B, use the data in the table to find the average acceleration of the plane over the time interval 5 to 25. So we're going to use the same formula we used in the previous question, but using values at 25 and 5. So if I substitute in values from the table, v of 25 is 2.4 and v of 5 is 9.2 over 25 minus 5, which is 20. And so this gives us a value of negative 6.8 over 20, which probably reduces, but I'm not using a calculator, so I'm going to stop there and put units on here, which again are going to be miles per minute squared. Final question, based on the values in the table, what is the smallest number of instances at which the acceleration could be 0 miles per minute? Justify your answer. Now, when we did this in class before, we did every interval to show the sign changes, and really we don't have to do every interval. If you notice from 0 to 10, on this whole interval, it seems that our velocity is increasing, and then somewhere between 10 and 15, it starts decreasing. And it decreases all the way until time 30, and then at that point, we seem to be increasing again. And so to save us a little work, we can find average acceleration on the interval 0 to 10, which would be 9.5 minus 7.0 over 10 minus 0, 2.5 over 10. And again, you could reduce, we can leave it like that. All that matters here is that we've ended up with a positive acceleration. When we do our next interval, average acceleration on 15 to 30, if I substitute in those values, 2.4 minus 7.0 over 30 minus 15, this time we get negative 4.6 over 15. And then on our final interval, average acceleration on 30 to 40, we can do the formula 7.2 minus 2.4 over 40 minus 30, which gives me 4.8 over 10. So we're showing a sign change here and a sign change here. And so we, to give an explanation for our answer, we need to say that because v of t is differentiable, it is also continuous. And then we can say, according to the intermediate value theorem, and remember we can abbreviate that IVT, acceleration equals 0 at least 2 times. And the work that we're showing here on the side should be enough to justify our conclusion. Finally, question D, the function f of t is defined by this function that they're giving us, and they want us to use that function to model the velocity and to find the acceleration of the plane at t equals to 23 minutes. So to do this, I'm going to pull up my calculator, and let me get this into the recording screen there. Okay, so I paused there for a moment to adjust my calculator screen. So we need to enter this function into the... And so I'm going to enter in, I need a calculate page. 6 plus cosine And remember, when you're entering this on the screen, you can use the variable that's given to you in the function. We don't have to change it to x. I'm sorry, I need to start this over because we didn't even do the derivative. They want us to use this function to find acceleration, and it is a velocity function, so that means we're doing a derivative. So let me start over. Menu, calculus, numerical derivative at a point. We're going to use the variable t because that's how our function is written, and the value that we're interested in the acceleration or the derivative at is 23. And so I've entered that in, and I'm going to say OK. Now I'm ready to enter my function. 6 plus cosine of t over 10 plus 3 sine t over 40. Let me just make sure I entered that in correctly. Looks like I did. And press enter. And there's our value, negative 0.407. Now remember, we could round that up to 8, or we can truncate and just leave it as a 7. So we are going to say that acceleration at 23, or you could say v prime of 23, they both mean the same thing, is equal to negative 0.407, and then notice it says we need to indicate units of measure. Again, those units are going to be miles per minute squared. All right, final question. Let f be a function defined on the interval -6 to 6. So they're telling us that this graph has endpoints. It's stopping here at -6 and 6. The graph of f prime, the derivative of f, is shown above. We are looking at f prime, and that's very important. If you don't have your table handy, you should get your table out so you can reference it while we do this problem. On what intervals, if any, is f increasing? Well, if I look at my table, if f is increasing, that means f prime is greater than 0. In other words, f prime is positive, which also means that it's above the x-axis. If f prime is positive and we're looking at f prime, then it needs to be above the x-axis. So here's how we're going to answer this question. We're going to start out our answer with what the question is asking. F is increasing on the intervals, and then let's put in the intervals where f prime is positive. That would be -6 to -5. -2 to 2, -2 to 4. So f is increasing on those intervals, -6 to -5, -2 to 2, and 2 to 4. I went ahead and split up those two intervals because at 2, the derivative is actually equal to 0. It's not greater than 0, so we need to split up those intervals. And then our question asked us to justify our answer. Here's how we're going to justify this. Because, and we're going to start building this habit right now, whenever we write because, the next thing that we're going to write is whatever is given to us in the problem. We always need to justify based on what is given. In this case, we were given f prime. So we're going to say because f prime, and then if you look back here at my translation of f increasing, I said that f prime is greater than 0. That's my reason, because f prime is greater than 0 on those intervals. Next question. Find the x-coordinate of each relative maximum of f on the interval -6 to 6. Justify your answer. Well, again, I want us to translate that from the table. If you look at the table, if f has a relative maximum, that means that f prime equals 0, and it's changing from positive to 0 to negative, because if I have a maximum, I want my function to increase and then decrease, which means my slope should be positive, 0, negative, which also means that my derivative graph should be above the x-axis and then 0 and then below the x-axis. So where does that happen? Well, let's look for zeros. We have zeros on our derivative at -5, -2, 2, and 4, and we're looking for where the graph is changing from positive to negative, or from above to below. Well, that happens right here. Here at -2, we're negative and then positive. Here at 2, we're positive and then positive. And finally, here at 4, the graph is positive and then negative. So it seems like the answer to my question is here at -5 and then also at 4. So here's how we're going to write the answer. F has a relative maximum at, notice it says find the x coordinate, that's all we're going to give, at x equal to -5 and at x equal to 4 because, and remember we're always going to follow that word because with what is given, which in this case is f prime, because f prime is changing from positive to negative at those points. And that's our answer for part B. Finally, part C. On what intervals, if any, is f concave down? Justify your answer. Again, go to your chart. F concave down, it means that the second derivative is less than 0. But remember, we are looking at the first derivative. If the second derivative is less than 0, the first derivative must be decreasing. And there's the bell. So where is our first derivative decreasing? It seems to be decreasing on this interval, and on this one. So f is concave down on the intervals -6 to -4, 0 to 2, and 3 to 5, because f prime, because that is what we're given, because f prime is doing what? It is decreasing on those intervals.